Today we're going to talk about enzymes. So the first thing we want to do with that is look at the definition. So the definition of an enzyme is a protein catalyst. So when we talked about macromolecules, we talked about an example of a protein was an enzyme. So there were lots of examples, but enzymes were one of them. And we talked about that it speeds up reactions. So the protein catalyst, remember catalyst means speeds up reactions. So you'll see that. I'm probably going to write that like 4 times on this. So a couple of just the highlights is what I like to call it about enzymes. So when you see questions about these and stuff, there's a couple of words that should jump out at you every time. Okay, so first thing, we want to make sure that we know that enzymes are proteins. So I've now written that twice. We'll see if we can get a third or fourth out of that one. Second one, enzymes are specific. Okay, so what that means is that they only work on certain molecules. So enzymes are very specific for the molecules that they work on. And they're not going to be able to speed up reactions with any molecules that they're not designed to do that with. So you can't just use one enzyme for a whole bunch of stuff. It's for one specific reaction. Enzymes are reusable. So we'll see in a minute why that is. So whenever they speed up a reaction, that same enzyme can go back and be used a second, third, fourth, fifth, 100th time. It does not get used up in the reaction like other things do, and we'll look at that. So enzymes, they speed up reactions. They do not create them. So what that means is that, like, for example, people who are lactose intolerant, they don't have the enzyme that can break down lactose into its smaller parts that would make us able to digest it. So they don't have that enzyme to break down lactose. Technically, it is possible, though, for lactose to be broken down on its own. It just doesn't happen fast enough for it to be able to go through our digestive system in time. So the enzyme helps make that reaction faster so that it can happen in the appropriate amount of time that life needs it to happen in. But it doesn't make that reaction. It just speeds up the process of it. And finally here, enzymes end in ase. Okay, so for example, lactase or polymerase. So remember that from biomolecules, when we're talking about the monomers of like carbs and proteins and stuff. So monomers, one piece, polymers, many piece, and polymerases are responsible for speeding up the process of building those polymers. Okay, so the reason why they are able to speed up reactions is this. So this is an energy diagram for a reaction. So the x-axis here is just the reaction progress, basically. And then over here on the y-axis, this is the amount of energy that's in the molecules at any point in time. So we have reactants and products. So we'll talk about this several times, but let's see, I'll use red. Okay, so reactants are red. And products are blue. So let's say, for example, we have, actually, no, I'm not going to make those that color. Yeah, you'll see why in just a second. Okay, so reactants and products. And there's a reason I have them. There's a reason I have them one higher than the other. The reactants are higher than products because the products in this case have less energy than the reactants. So you can think of this like breaking down your food. So that lactose and lactase example, let's just go with that. So lactase breaks down the sugar lactose, which is a combination of two sugars. Okay, so this is lactose. And when it gets broken down, it gets broken into glucose. Oops, I spelled that wrong. Glucose and fructose. Okay, so what's happening is in this reaction, you have food that's being broken down. And as you break your food down, energy is released. So the lactose has more energy than the individual sugars that make it up. So in a normal reaction, what happens is you have to kind of stretch the molecule. You have to put some energy in to stretch the molecule and make it like a little bit uncomfortable. And so you're adding a whole bunch of energy, and then it's able to release its energy to the products. Okay, so this stretch of energy here that you have to put in is called the activation energy. Okay, so it's the energy that's required to start the reaction. And even though the reaction ends up releasing energy, you do have to put some energy in just to get it started. It's kind of like when you're burning campfire, for example. So once you initially light the campfire, it's good to go, and it's releasing a lot of that heat energy, but you did have to use something to get it started. That was kind of the same idea as that. So this is the activation energy without lactase, the enzyme. Okay, so what actually happens is, if you have the enzyme, it starts and ends at the same place. I can get my color to change. So it starts and ends at the same place, but it just doesn't have to go up as high. Okay, so if you have you know what, I'm going to do that in blue. So it just doesn't go up as high. So it starts and ends in the same place, but that activation energy, this is the, so activation energy is EA. I'm just going to use that for space purposes. So this is the EA, activation energy with the enzyme. So it's lower. So basically what that is, so think of it this way. So the activation energy for a campfire. So if you have a campfire, and you're trying to light it. So if you just have a match, that's all you've got to light it. You would eventually be able to get it to light, right? You would have to put in a lot of effort to get it to light, probably, versus having a can of lighter fluid. So then you spray the lighter fluid on the wood and then you use the match. That's a lot easier. You start with wood and you end with ashes and you get all this energy out with both of those reactions, but if you have that lighter fluid, then it makes it happen easier and faster to begin with. So in that example, the lighter fluid is kind of like the enzyme. So it makes it to where even though you have the same reaction happening, it takes less energy to get it started. That's all it is. So it basically, what an enzyme looks like, yeah, we'll do it this way. So an example of an enzyme, maybe there's this little thing that's got like a little oval and a little triangle thing here. So this is your enzyme. Okay, so let's say we have this thing we wanted to act on, and it's shaped like an oval attached to a triangle. So that makes sense because it can fit in to that space, right? So let's see. Can I move it? There we go. Okay, enzyme. Okay, so then when it fits in, what it looks like is something like this. Bonded to that triangle. So it fits perfectly into that space. And then what that enzyme does is it breaks that bond. In this case, it doesn't always break bonds, but in this case, that's what it's doing. So in the end, what you get, now I have to put this enzyme a little bit lower. So in the end, what you get out is a little oval going over this way, and then a triangle coming out this way. So you started with this piece that had two parts to it, and then when it docked into the enzyme made a nice comfortable place for it to have that reaction and break apart. Okay, so in this case, there's a name for this. This is a substrate. Okay, so that's a substrate here. And then these are your products over here. So it's what you're getting out of the reaction. Okay, that was messy, but it works. So the substrate is what goes into the reaction and bonds with the enzyme, and the products are what come out. And then notice there's this little section here of the enzyme here that I've just outlined in blue here. So that's what we call our active site. So that's the site that is extremely important to have the correct shape, because it needs to have exactly the same shape as the substrate, so the substrate can fit in there so that it can do its reaction. So this is just a very, very, very general example of an enzymatic reaction. So the enzyme, you notice here, it stays exactly the same. I literally copied and pasted it because it does not change the entire time. The entire time is completely unchanged. So it's unchanged. And it can go and do another reaction if he wants to. But the substrate has been broken apart into the products. And it could be backward. It could be the substrates were separate and then the products were together. But either way, they're fitting perfectly into that active site on the enzyme so that it's a nice comfortable spot for that reaction to occur. So the enzymes make it easier for that reaction to happen. They don't make that reaction happen, but they do make it easier because they make it require less activation energy to get the reaction started. So to go over this hill here, it takes a lot less energy to get over that hump to get the reaction started, basically. So that is enzymes. Later, we will talk about what happens if you, or how to get the shape of the enzymes messed up. So here, just make a very, very, very important point here that the shape of the enzyme is everything. The shape is absolutely everything. If the shape is messed up, then the enzyme cannot do what it's supposed to do because it doesn't fit with the substrate. So, um, we will end up looking at the kinds of things that can cause that to change shape. And it happens to enzymes, and it also happens to other proteins as well. So that shape is extremely important because that active site and the substrate have to be able to fit together. And they lower the activation energy, which makes the reaction able to happen faster.